All right, so it is my privilege to introduce Niall Gaffney. Niall has a background in astronomy, actually a really strong background in astronomy, and as I like to consider it, it's really where big data came from, because you don't get much bigger than that. Niall has had a really interesting career that I always like to hear about from him. He's been involved with almost every large astronomical telescope mission that NASA's put through, with the Hubble, with James Webb, Kepler. So if there is data that has to do with astronomy, there's Niall. Which is why we brought Niall in as our director of data intensive computing here at TAC. So with that, let me introduce Niall, and Niall, so the stage is yours.
Thank you, Charlie. Yeah, so I actually did come from a different background, and I think a lot of people are sort of in this phase right now. You know, my background is purely on the data side, but the computational side of data, of producing products and results that are important for all the research that we do. And
you're not sharing.
I'm not sharing?
No.
It says I'm sharing Microsoft PowerPoint.
No, they're not getting your content. So they can maybe reshare.
Stop sharing.
Yeah, we're sharing.
Okay, you said they weren't getting content.
We see it in now, so.
How about now?
That'd be perfect.
Is that good?
They said they saw them, but I know we're in.
We're in? Okay. Yes, and so I think that, well, to sort of throw back to what Noel was talking about, the fifth paradigm is going to be fixing how you get network presentations in printers. I think those are the biggest challenges ahead of us. But in all seriousness, I think, you know, coming through all of this, the PETASCALE has enabled so much science that we can do today that it's become, as I have in my slide title here, sort of the new black. It's everywhere that we look. And in fact, you know, it's become a mainstay, whether that is in a data sense or in a simulation sense, to what people are doing. And of course, we're now moving on to exascale, or as we like to here in Austin call it Texascale, because, you know, our congressmen always do like to hear about Texas more so. So it's good for funding to do things like that. But we sort of are very interested in how this is all going to scale out from the PETASCALE environment and lead us to, you know, I think it's fantastic to see flops go up, but larger results and better results. And that's really the goal, I think, of all of this scale, is not just to get flops out of things, but in order to take these complex systems and utilize them to make the science and discoveries happen. So, of course, when most people hear about high-performance computing these days, the things that they think about are large simulation works. And so here are three that I know we've been working on here at TAC. Sort of over to the left-hand side is windmills, and looking at sort of the turbulence that comes off of the windmills to, you know, optimize airflow around the turbines and the capture of energy. You know, very important for powering these supercomputers, which are very power hungry at this point. So sort of it helps us make our systems more efficient by doing that at some level. The top right, that's an image that we have of sort of tornadic activity, something very important to folks a little north of Austin, mostly in Oklahoma, and around the Midwest. And so, you know, a lot of the climate modeling and things that we do as on different scales, whether that's local scale or global scale, are things to think about. And the last one down there is sort of the astrophysics models. And this one in particular was the two colliding black holes that LIGO discovered a few years back. And that was a simulation that was done by folks coming from Cambridge in Stephen Hawking's lab to both verify the results, but then also to tune their models in order to understand better the physics of what was going on at the actual collision. And all these things are really important sort of things, but there are many other things that come out of high-performance computing these days that I think people don't recognize. Or if they do, it's because they're involved in them or because they don't understand that this actually is high-performance computing. And I think that's a good thing, that there's a lot of this abstraction layers, a lot of ways to make these things work better for people. Sort of down here on the left-hand side was, that's a both a combination of simulation, but then also of data coming through sort of machine learning techniques to identify features in the brain of, in that case, it was glioblastoma, but looking for tumors in brain scans and seeing if we can do better than what people can do by eye. And in the end, it turned out it was true that we had better efficiency at detecting things than you could normally. There's also things like protein folding, which is the top center, which is a problem where you want to understand how different things can dock into different proteins, which is important for drug uptakes. And so there's a lot of computation in the chemistry that goes around that. To the right, I went ahead and did LIGO twice, largely because I am an astronomy nerd, but also because we did more than just do the simulation work. A lot of the throughput work and tuning the performance for what they did was an important facet towards getting the results that LIGO had when they started it back up a couple of years ago. And in fact, working with them through the centers through Exceed, they were able to get a higher performance out of their code by optimizing things better. So not only were we able to, this is sort of that punchline for, not only were we able to get them up and working at PETASCALE what they were already, but we were able to get them more efficiently working there. And the last is just because I'm a space nerd, we're working with a Firefly company up in a little startup company about 60 miles north of here that are doing new rocket designs. And a lot of the design work that you have to do around the CFD components needs high performance computing. These are things that most people outside of the field probably don't recognize are important, but are sort of key facets to this. So Gordon Bell gave a lovely introduction to the introduction of computing and where things started. I don't want to harp on that too much, but I did want to sort of paint through how things have evolved in computing, and then parallel after that, well, not parallel, that'll be serial, after that, go through and talk about some of the technologies that are helping us tackle the problems that all of these changes have introduced. Because I remember when there were craze here at the University of Texas. In fact, their former director, Jay Boisseau, worked quite heavily on the XMP and YMPs that we had in grad school. And it was a simpler time back then. You programmed in Fortran, you were worried about some vectorization, and you moved on. And is there just okay? So we sort of reached that end of Moore's law, the scaling of processors, and went to this parallel processing era here. And so to the right, that's actually our current director built that system, that is Grendel, which was the follow-on to Beowulf. And it was white box computers and learning how to do things in parallel. This wasn't something that we chose to do. And in fact, I think Gordon would support that. He would say, look, if we could do everything with shared memory and vectorization, it'd be great. But we've adopted, and we've had to scale out because of the nature of the industry. TAC has been here for going on 17 years now, and we've been sort of at the forefront of a lot of this parallelism. But you see in the systems that we've laid out, for both the University of Texas and for the nation, that the problem is becoming more and more complex. So in 2003, TAC rolled out the first Linux cluster for open science, which is sort of pictured there with the blue lights. And it was a much simpler system than what you see today, simply because you had single processors with memory on each individual system. Scaling up from there, we deployed Ranger, which was the multi-core nodes, and InfiniBand Fabric for message passing infrastructure in there. And things became more complex because you had to worry not only about what was going on each node, but you had to worry about the communication patterns between the nodes. So suddenly things are becoming harder and harder. And then we move on into even more complex systems, which have been sort of the state of the game for the past 8 to 10 years. And you get everything from Stampede, which was our successor to Ranger, which was a very large multi-node system, but it had accelerators in it. And at this point, there was a debate, I guess, at some level between NVIDIA and between Intel as to what you would want to do. But in Stampede, each one of those Sandy Bridge nodes, which had 16 standard Xeon processors in them, had Xeon Phi processors on PCI cards. And this was great if you could get the code to work well in that environment. But this required you to have now a third layer of abstraction, that you were not only just talking between nodes, but you had to talk between the processes on those nodes and the cards within those nodes. And that sort of is the complexity of the accelerators, which leads to having languages like CUDA and OpenACC, which allow you to abstract some of those layers out, but makes it more complex because you are managing more and more systems all at the same time. The other piece that came up in 2015, and I put this in here not only because I thought Wrangler was a pretty cool system with 0.5 petabyte of shared flash memory with a theoretical read rate of 1 terabyte a second. No process could really do that. But this was the first system where we had more unlimited I/O. And I find that very important because there were several problems that we pulled off of Stampede, which were taking up hundreds and hundreds of nodes just to get the I/O patterns through and move those onto a system that has this flash memory. And they were able to not only reduce their footprint, but improve their time to solution by factors of 4 or 5 by having this other piece of hardware in there. But again, that means you've got a different storage layer in there. So all of these things are just different layers coming in that are going to make the problem, I don't want to say more difficult, but you do have to sit down and think about your problem and break it into the right pieces. And then in 2016, we deployed Stampede 2, which has 5,000 plus nodes, each with 48 or more cores, multiple architectures in there, so both Xeon and Xeon Phi nodes, large amounts of memory, but of different speeds. And so actually fitting your problem onto a system like that, while you can do it simply because it is all x86 code, to do it efficiently requires some work. And that's sort of where I think this institute is looking to help people with, is how to abstract their problems correctly or more efficiently and get to scale. So the other thing, and I think this falls in with these change in the third and fourth paradigms of computing that was mentioned before. I've met Jim Gray a couple of times before he passed, and great fellow, but really sort of painted this picture that there was more to computing than simulation, and that was his fourth paradigm. But I would actually argue that it's become more just the third and fourth paradigm kind of together, because there's no simulation today well, there are very few simulations today that give a simple answer. There are complex answers that come out of these things. And so while if you've come up through observational astronomy or biology, you've worked on analytics quite heavily. In fact, that's what you did most of your career. In grad school, I called it plotting X versus Y, which was taking all your variables and seeing which one's correlated, going from there. But we've brought in this machine learning and AI portion to this. And all of this has now allowed us to sort of computationally tackle all three of these problems together. And I would argue that modern science is actually all three of these pieces put together into a single paradigm. And so I think that's going to be the challenge over the next 10 years, is how do we do this most efficiently? How do we do this in a way that domain experts can bring their expertise in without having to understand everything that is MPI or neural networks. And these are the challenges here ahead of us as a community. In addition, one other challenge, and so I'll get into sort of more technical things in just a second, but the other challenge is that this is the world that most researchers live in today, which are notebooks or graphical environments. And we have a whole host of people who are coming up who are not accustomed to batch processing. You can throw it back to sort of instant gratification isn't fast enough, one of Carrie Fisher's greatest quotes in movies. But it is, everybody expects everything to be cloud-like and come back very quickly. And that's a challenge that we have to tackle, is how do we allow people to use these things, which can take days to months to produce results, but an environment that they are used to and feel familiar with that may not be a Fortran program or the command line. So these are other problems that we're going to have in the PETASCALE and the exascale going forward, is not just scaling things up, but making these applications more approachable. So parallel programming, I'm sort of take a step back here and go through some of the basics of this. So well, I'll just say, this may be a little bit sort of a low-level introduction for some folks, but I wanted to make sure that we covered this so that people can move forward. So parallel programming really is just, you know, the Tom Sawyer story of pavement and fence. It gets done faster if you have two people working together. And the key is not just more brushes, but working together. And so you can either paint the fence faster, or you can make a larger fence get painted. And so that's really what we do in parallel programming. And so that's the simplistic version of that. That's sort of, if what you're doing is embarrassingly parallel, you can just divide jobs up and everybody goes off and does that juggling everything in the air. I really like that slide, all at once, and they come together at the end and present their results. But then you get into sort of this first level of real parallelization, which is the vectorization. And that really is sort of like, you know, running a combine across a field. You have, you know, multiple plows going through the field all at the same time. And so this leads to an orchestration that takes place that does what you need. And in fact, you know, vectorization is about making sure that your inner loops are done in a way that maps to the system's way of thinking. And that's sort of the first hurdle that a lot of folks have to understand as they're going in, is that the order that you operate on a vector makes sense, has to make sense to the computer, not necessarily to yourself. And that has to do with how things are aligned in memory, so that pieces can be pushed through this combine, which cannot be reconfigured to plow different style fields, but actually can go through and do that. So it's sort of this first point where you've gone from this pure system like Fortran, where you're teaching it what to do the way you think, and now we're having to start to think the way that the computer thinks to optimize things. And the reason for that is this simultaneous instruction multiple data problem, or SIMD as people refer to it. And so today, you know, going back to the craze, but on all systems now, really this SIMD capability is the power of parallelism that most people are taking advantage of. And this is for CPUs, it's for GPUs if what you're doing is a lower precision computation often, which is true for machine learning and deep learning. Pretty much any sort of programmable processor other than the FPGAs. And so the point is, you have to feed both of these arrays in the same style, aligned in the same way in memory, so that the vector processor can go through and take those four elements in this case and add them together and replace those values in array B. And so this is the basics of vectorization, which was really all you had to do back when I was getting started or understanding about all of this, and is still very important today. And so here's a kind gentleman sitting on a Cray, probably reading about how to do vectorization on the Cray. And you know, it's been a long time since that was the fashion statement of the day. So I'm sort of, you know, glad that we've sort of tackled much of that. Shared memory is sort of the next problem that you run into, and this is where you have multiple cores, all on one system that can address a common pool of memory. But this has perils as well. The challenge is coordinating between these cores doing all of these things so that you don't run into any sort of race condition, where writing to one piece of memory or another piece of memory is corrupted by another process. And so this is where applications need to understand thread safeness, and this is where technologies like OpenMP come to play, which is a programming model that helps abstract out those pieces and allows you to program your threads in a safe way so that hopefully you don't run into problems with memory corruption for multiple threads. But it's managing these threads that's sort of the complexity of it. And so a lot of what's going to be talked about in the Institute are technologies and pieces that enable in more standard ways to go through and do these things, these complex things, in what is hopefully a simpler method than it would be if you had to write everything from scratch in Fortran. And then you run into distributed memory, which we were talking about earlier, which is really where the Beowulf systems came in, where you had, back then, a single core, typically in a white box PC computer, that has its own RAM that's accessible only by that core. And what that then requires is the ability to communicate between these cores and pass data back and forth. And that's where this programming model that is called MPI, the message passing interface, came to be, that allows you to break your problem up and have communication done most effectively for the problem that you have. It doesn't mean that if what you have is a mesh computation going on, that all pieces have to be able to talk to all other pieces at the same time. It allows you to break your problem up into components, sort of like a jigsaw puzzle, and talk to the right nodes at the right time. This hopefully allows for minimizing contention between nodes. Not every node is going to run at the same speed. There's a lot of issues in grabbing things in memory. Back in this time where it was a single core, you didn't have as much of a thermal problem as you do today. But it allowed you to sort of go through and work through the problem with separate copies of the same executable operating together as though it was more of a symphony than a single machine. And then things got more complicated. And I think that's sort of the theme of advanced computing these days, is that things are getting more complicated. So most large clusters today are a hybrid of these models, and sometimes an even larger hybrid of these models, because they may have things like GPUs or TPUs, so the tensor processing units, involved in all of this. And so in this model, each node is a multi-core shared memory computer running its own operating system. And each of those nodes have to manage the threads and processes that are taking place on that node, often on two separate portions of the central bus, so that pieces of RAM may be owned by different pieces of the CPU or more quickly accessible. So pinning data to cores is an important thing. And in fact, if you have then GPUs, TPUs, or other things that are going across the PCI bus, you have to then manage all of those pieces. And so this is where things like OpenACC and CUDA come into play to allow you to orchestrate the on-node processes, then using the thread-safe OpenMP layer to orchestrate everything on each node, and then pulling all that together with the message passing interfaces to orchestrate across the entire cluster. So as you see, we've now got a very complex system. And if what you're trying to do is add two vectors, it's not as simple as it used to be. And so that's, I think, the challenge ahead of everybody here, is to understand how to best abstract their problems, break them up into pieces today in ways that may not be the way that you think, but may be the best way for the computer to handle the problem. And then to create layers of abstraction that help you explain it the way you think. I wanted to put this in here, which is Frontera, which is the new number 5 system we just deployed here. But it sort of shows, I was talking about the complexity coming together. All of this has come together in this system. And I think this is true, not just the ones that we're deploying here at TAC. This is going to be every system in the world. First of all, a very tall system. The gentleman in the blue shirt is about 6'6". So the density of the system is pretty high, and orchestrating all of those things is going to be hard. But it includes 3 terabytes of NAND flash, which is sort of showing that, remember I was talking about Wrangler and the fact that high throughput I/O is very important for some problems. We now have multiple storage systems on this system, and those different storage systems can be tuned for different problems. So again, another layer of kind of complexity. Where do I compute? Where do I put my data? And all of these things are things that need to be explored. I don't think there's a rule of thumb. It's not like we can have a Microsoft wizard, Clippy can't come out of the corner here and tell you, you really should be using Flash. You need to learn how to do these things and experiment with these things. And so a lot of then what comes from these things, which is sort of going to lead to the future of computation, have to do with linear algebra kernels and for handling large parallel matrices, because really that's what the nature of all these problems are. And so there are going to be many different libraries and different things that you can use to help optimize code, but they all, including CUDA or PETSC or FFTW, make you bring the data into those libraries in ways that they process things best. And so, that's going to be that's the orchestration problem. And for each one of these layers and each one of these wonderful pieces of technology, there's another one of these sort of kernels or libraries that people have to use to get their results. And we'll talk about many of those here at the Institute over the next 5 days. Just wanted to sort of talk about a couple of the problems real quick. Again, I'm an astronomer, got to be an astronomy nerd. Some of the other things that people have done with these large systems is to do the simulations, but then also the projections of the shadow cast by the black hole at the center of M87 that came out a few months ago. And it really is sort of shows that there's this marriage now between both observational and theoretical simulations that are taking place in astronomy. But in addition to that, in fields like tectonics here, where people are trying to predict aftershocks, a very complicated thing to do. I think the last one, we were still surprised by how the aftershocks took place in California. But these are problems that are going to bring together very quickly the data and observations as well as simulations that have been run to come up with real predictions for people in the field during any of these events. My sister's a search and rescue person here in Texas, and we've done some of this around flooding around the Hurricane Harvey. And these are going to be very important problems for us to tackle moving forward using simulation and data put together. Which sort of leads me to sort of talking about data. And so this is my comfortable wheelhouse, but I was put this together here to sort of talk about where AI and machine learning is going. And I think, this basically, I think, talks to what that fourth paradigm is. It takes tasks that are easy for people to perform, but hard for people to describe formally, and allows those things to be done in a computational way. That's one way to put it. The other way to put it, and I was a graduate student once, and I recognized that there was a lot of work that I did that was that. And so a lot of what artificial intelligence is doing is a lot of the work that we used to do by hand and automating that. And so I don't want to call it an automated graduate student. I think that's derogatory to graduate students, but it really is automating a lot of the work that 40 years ago was done with a piece of paper and a pencil. But that's sort of the overall of AI. Deep learning is a particular portion of machine learning algorithms, which have multiple layers of nonlinear processing units that are used for feature extraction and transformation. And that's sort of a long-winded way of saying you have a bunch of processes that can go through and without equations of state or other descriptions of the system, try and find characteristics inside of those systems that can be predictive. And for some things, this is the only way that you can go through and understand things. If what you're trying to do is something that is not governed by states, equation states, and cannot be simply modeled, say Twitter feeds, this this is an area where going through and using things like natural language processing and then sentiment analysis, which is all based on deep learning processes, you can actually get results coming from areas that you could never compute against before. Sometimes it does a little better than what you do by hand. And in fact, that's, I'll show an example of that in a little bit, but that comes to exploring large simulations of weather models where it does a better job than what you can by hand because it can take into consideration things that can't be modeled correctly, such as the ground and how buildings and other things, heat bubbles around cities can influence how storms take place. And sometimes you need both, because sometimes it's that marriage of the two that come together to really sort of get things going. So I'll go through this history real quick. None of this is new, and I think that's sort of the point of all of this computing that we're talking about here, is that this is stuff that goes back, you know, as long as I do, if not longer. And so back in the day, cybernetics was a thing, which was basically just doing a reaction feedback loop for a sensor. But this led into this notion of connectionism and neural networks, which took off sort of in the 90s. And neural networks allowed sort of this abstraction of how the brain makes decisions and how you can take large complex systems and feed them through a series of equations and come up with predictions. And that's really was in the 90s what people wanted to do, but it really hasn't been until the past 10 years that the capacities and capabilities of systems that we've had allow us to do this, apart from simple problems. And I think that's sort of why deep learning sort of trails in well, there are multiple ways to do deep learning and machine learning. There's not a single MPI. I think that's one way of saying it's still an evolving field, and it's sort of what it was when message passing was younger on the first Beowulf clusters. Of course, most people think about self-driving cars when they hear about machine learning. Self-driving cars are great, except there was one time I was actually trapped between two of these in my neighborhood where Google was testing out these Lexi, and they drove like nervous 15-year-olds. Why? Because they were learning. And so at some level, that was bothersome while trying to make that right-hand turn. It tells me that they are sort of learning, and they're learning in a way that was familiar to me because I recognized it. They also are known for doing things that can't be modeled. The game of Go, the game of chess, or the game of Dota, for those of you who are much younger than me, these are all things where you can't necessarily write a model for how to solve this problem. And that's where a deep learning algorithm comes into your advantage. It's all over the place these days. It's being used in astronomy, drug discovery. There are people who are finding new materials or potential new materials based on deep learning of all of the publications coming out of those fields and finding similarities in materials that had never been thought to be put together. Similarly in biology, I know there are things happening there. And then people are doing things with these deep learning and tensor networks, which used to be reserved for high performance computing. So this is just one particular, I think it was mostly the astronomy conference, astronomy and physics, which all has these equations of state. But you know, here Milos Vodasinovich, who's here at UT Austin, was using TensorFlow to solve PDEs with deep neural networks, cosmology and machine learning, a cosmological emulator utilizing generative adversarial networks. I'll talk about what those are in a minute. But this is using technologies that we hear about in deepfakes or whatever else that the news tries to paint AI as being scary, and using it in ways to actually drive computations forward. So I want to motivate real quick here, go through what deep learning is. I don't expect everybody to get all of these pieces, but the first piece of deep learning goes back to, as I said, as a graduate student, plotting X versus Y, and then fitting something to it. And that's called linear regression. We've been doing it for decades, and there are many methods for doing this, but they all come down to having some sort of a loss function. That loss function is based on the previous iteration of the fit. You go through, you improve your fit by estimating how much you need to move your solution based on the first derivative loss. costs. So if you think about it, in a two-dimensional problem, you basically slide down until you find a local minimum, and then if you're good, you expand out past that to make sure that you don't find another local minimum, and you sort of iterate on it. So from linear regression to a neural network, I'm going to do this with pictures of cats. You take a picture of a cat, you turn it into a vector. The machine doesn't know what it's a picture of a cat. And then you've got some linear model behind that that makes some prediction. And so in this case, it may be color balance, it may be, seeing how fast things change across different areas. All of these pieces can come together with how this string of numbers are put together. You make a prediction from that. And then what makes it a neural network then is that you have this activate function. And the activate function will light up as a true when a particular prediction hits a particular level. So it's basically a voting algorithm, if you will, that can go through in the neural network and allow you to have this hidden layer of all sorts of different fits and pieces to that, which can then help you improve your overall picture of that cat through multiple different ways, coming out the other end and being able to say, yes, this is a cat, or no, it's not. And of course, you don't want to just do that once. You want to then have an iterative sort of model on that, because if you just do it once, you're not going to be able to tell the difference between the cat, the dog, or the hot dog. But you're going to be able to go through and teach this thing over time what these things are. And this is sort of how we learned. But now I have these three different images here, and they're labeled. And now I want to gather, say, 10,000 more of these, and I use those and their labels to sort of go through an iterative loop here to train this neural network and teach it how to weight different things and how to activate correctly, so that it's able to, when you give it later on another instance of an image, it can make some prediction of that. And the image, as far as I was concerned, doesn't have anything to do with what it is, it's just a vector of numbers. And that's really the thing. This is the simplest example. This is what everybody sort of goes through, or handwriting recognition, if you ever do a course on deep learning. It's great, but it is just a vector of data. And this is driving many pipelines that are out there nowadays, where you have data sources, say a telescope, at a facility that has gone through and trained, based on the images that they've had in the past, a model so that they can do evaluation in real time. And so that's really cool. If you're trying to detect supernova, you can actually have it very quickly, look at every frame that comes off the telescope, and predict what's going on. But we're talking about petascale computing here. I missed the slide here, so I will step back. That data source could be a large simulation. And the facilities and labs could be observations that support or disprove some of those simulations. And so it's actually going to allow you to go through and evaluate whether the predictions that are being made by that particular execution and large data set are realistic or not. And that's sort of the power of bringing together machine learning with simulation as we're moving forward. The other piece of sort of machine learning that I want to cover is this generative adversarial network. There are other pieces in here I could have gone into. I encourage people to learn more about these things. But this adversarial network is sort of interesting, because what it does is it actually takes two different networks and makes them compete. And so in this case, you may have a bunch of real images or real data, and you have a discriminating network that is able to take things that come in from some other process and discriminate, say whether it's better or worse. You then here have, in this case, some noise vector coming in. That noise vector is just going to be trying to change things to say better or worse. This is sort of the eyeglasses test that you take at the eye doctor. And it feeds that into the network, which may create some data, it says fake images here, and then uses that with the discriminating network and sort of the cycle to improve the noise vector, so that eventually you have a model that predicts what things are what's going on. This is the source of all these.
Got me thinking about my full-time employees. They're building.
I don't know if you all can hear this or not, but this is one of those deep fakes where they took some video, Barack Obama, and changed his mouth movement so that he was saying things he wasn't saying. Now, they didn't do this nefariously. This was sort of done to prove this point. But the point is, they are able to take some data, which is the sound of his voice, and use that in a way to change the model, which is the image of him, to match the voice. These are things that may be very powerful in the future in bringing together models of data. And I think this is a challenge to all of us, is how to do things other than cat videos and all the other great things on the internet, but turn these into actual science results. And so I see this as a new field that is going to challenge us in the future. But this is sort of the pulling all this together here. Honestly, in the end, these are all just large matrices. And in fact, they are low precision matrices, not necessarily high precision matrices, because it doesn't matter whether you get the third decimal point right. You just really want to have these networks fire or not. But the math is still the same. The other thing that we've seen is this change in the field. GPUs are currently, what everybody wants to use for machine learning and deep learning, unless of course they happen to be at Google, where they have these specialized tensor processing units. But even the new Intel chipsets are starting to do lower precision and do other things in similar ways. And this actually reminds me of, I hate to always go back to the early 90s, but you go back to your grad school days all the time. This is no different than it was when you had floating point accelerators in your computer. Right? All these accelerators eventually wind up, if they're any good, in the system itself. And so I'm interested to see how these things come together. I'm also interested to see how all of these different environments, whether it's TensorFlow, PyTorch, you can go, it's an Intel NASCAR sort of slide when you put it out there of all of the different architectures that are out there, or frameworks for doing deep learning machine learning. And I'd really like to see those all come together and perhaps even be a single infrastructure for doing this in the same way that we do high performance computing. Same sort of message passing architectures, same complex nodes, just able to work on different forms of data. If you can do that, then you can actually have a problem that works in all three of the areas. I'll get to that in a second. All three of the areas that I was talking about earlier on the same system. And the great thing then is you don't have to move data. We all know that data motion kills. And so the real, if we can do this, I'm always accused of wanting a pony. But the real pony here is to have a system that can do all of this all together at once and have it done in a way that users can tackle that. I already did this the other time, so yes, I know my equations of state, but here's how I can actually use machine learning to do interpretation. But as I said, this isn't new. Cosmological models have been doing sort of machine learning, deep learning to find feature detection. So recognizing what an early galaxy looks like in something like this. This is the Renaissance simulation, which was computed on blue water some years ago. It's a large simulation, and actually going through this as a graduate student would hurt. But this allows you to go through and do feature detection and projections and gain a better understanding of this very large data set that was created. And then other things that have been really advanced by these techniques, these combinations. This is sort of scaling up weather models to predict hailstorms. And for those who live a little north of us here, this is around the Dallas-Fort Worth area. Hailstorms can be a very big deal when you start talking about softball-sized hail. And those are very difficult things to simulate. And so being able to discern between those and understand not just 2 hours ahead of time, you better get your car in a garage, but actually prepare for it. The whole city is very important. And the University of Oklahoma folks have been able to combine their ensemble weather simulations with observed historical data and give better weightings to that ensemble to improve its predictive nature. And the predictive nature of their models have been extended from 2 hours to 24 hours. And if I have 24 hours to prepare for a major storm, I'm much better off. So I hope that gives everybody sort of an introduction to both the simulation portion here, but also this analytics and machine learning portion, which I think are very important and are going to be driving all of these fields forward over the next few decades. As we scale up from petascale to exascale, it's only going to become more complex, and I think having more tools in the tool belt will be important to tackling these big problems as we move forward. So with that, I'll end a little early here. Take any questions if people have questions about things. And,
Yeah, we have a couple questions. One is from Pavan Mehta, and they'd like to know if you can elaborate on hybrid architectures and quote each node running its own operating system. And I think they'd like to elaborate a little bit on that.
on the hybrid one. So that's sort of each node that we have here, at least at TAC, is running an independent operating system. It actually has a local OS, a local disk. It's not working in that classic Cray way of just tasks going to nodes. And we found that that is an approach here at TAC that allows us to tackle things both more flexibly, but also it's a bit more manageable, I guess is one way to put it. Yes, we do have to manage the systems a little more because we are pushing packages onto the nodes themselves, but the performance of actually having all of the codes and pieces locally, rather than having to come in over the network, improves start times more than anything else. Once you have it in memory, it doesn't matter, but it does improve start times of some of these large jobs. So that's where that OS comment came from.
Another question is around slide number 37. They would like to know why you called it a prediction and not an inference.
37. It could be because partially because it is an inference. You are inferring an answer from the data. And so, yes, I think that would probably be an improvement to my slides to call it an inference. So I thank everybody for copy editing. Honestly, it is you were inferring what that is from the data.
Correct. Also, a question from Petro Junior Belmont. He would like to know, you mentioned GPUs versus TPUs. Is there one board that has more advantage than the other?
It depends on your data. It depends on what you're doing and what you're predicting. I haven't really had my hands on TPUs. We do have some access to them through the Google Cloud. So that would actually be a good question for Zhao Zhang here, who has done a few things on that. The difference is, we had an example of this is we're doing some ImageNet computations just to see how well we could work on Stampede 2, which is a CPU-based system. There are no GPUs there. And for the right problems with the right tunings and the right batch sizes, all of which are important things, how you break your problem up, we found that actually the speed of training on Stampede 2 was as fast as an equivalent one on Volta V100s for double the nodes. So that means if you had 1,000 nodes of GPUs, 2,000 nodes of Stampede 2 could keep up with it. The interesting thing there, though, is that you've got 2,000 rather general purpose nodes that are able to keep up with that. Now, that's just that particular problem. If there's some inferences that you're doing, then yes, the GPUs are much better because they're much better doing low precision. Whereas you can keep up on something that is doing 64-bit floating points much better on a CPU-based system. The tensor processing units, I think, are again their forte is going to be going to lower precision. But as I said, I think the Intel folks are doing that, and I'd really, at some point we'll stop calling them accelerators and we'll start calling them all processors, and then there will be a new round of accelerators. It's how this works. But it's an experimental thing. And in fact, on Frontera, we have access to TPUs through the Google Cloud, and to allow people to do exactly those sort of experiments. But I think it will be much more of an experimental thing. Speaking as an experimental scientist, correct me if I'm wrong, computer scientists, but often it depends on the data.
Right, looks like there's two more questions here. From Dario Demontes, can you elaborate a bit about neuromorphic computing?
I don't know enough about neuromorphic computing to be able to elaborate more on that. That's actually one of my blind spots right now. I know that it shows great potential, but much like quantum, that potential is sort of in a limited scope. It's not as general purpose as many of these techniques are here. And I make my living on the general purpose leading edge of this, so I will have to dodge that question. Hopefully somebody else can pick it up.
Okay, actually, sorry, another question just came across. We have two more questions here. So regarding the topics of this talk, what, I guess in your opinion, will be the next computing paradigm? We know that data intensive computing is what the current shift is happening, but what's coming next?
I think it's the merger of the two will be part of it. I don't think that's a paradigm. But I also, I don't want to get into, that was the day that cybernetic computing started. But I do think that that's part of it is we can act as monkeys typing on keyboards to produce Shakespeare. And we've done a pretty good job of it, but the computers will do a better job of working themselves. So the next level may be, computations that actually improve themselves. That's what I would like to see, because I really think we're good at thinking and they're good at doing. And if we can split those problems in a better way, then we won't have to have people learn all of the nuances of what SIMD computations are. And we can do other things. So that's for computer scientists to really change the way we program these things.
All right. It looks like we have one last question from Suyash Tandon. In modern HPC, while the increased computing power allows us to compute bigger and more complex problems, what about other limitations, power consumption, memory bandwidth, etc.? Should modern applications of hybrid systems also focus on these issues at the software level as well as the hardware level?
I think they're going to need to. The wattage is while getting better as far as the number of watts per flop is getting better. That's going to always be a limitation. The complexity of the memory models around these things. I mean, honestly, in a dream world, we would have exactly what Gordon Bell was talking about: is the infinitely fast processors all running on shared memory. Everything after that is a limitation. And so, yes, we have to make things run better and optimize those things. You can talk to folks up and down the hallways here and at NCSA and San Diego and at Pittsburgh about what's wrong with modern architectures, and everybody has a story. And those are all things that you have to tackle to make these things work that seem to change every time they release a new version of a chip. And that's a pain point. So I would almost say stop reinventing chips to make everything just x86 architecture and make it as simple as possible. That'll never work. Again, that's my pony. But yeah, there's always going to be that. And there's always going to be a need for some large group of people, but perhaps a stable number of people who tackle those problems so that these systems do what they can.
And it looks like one last question just came in, and this might be the last question. On regards to data-oriented building of human knowledge, all right?
Mm-hmm.
What are the alternatives to it? I think you said, especially considering the so-called E-rooms law, I'm not familiar with myself, where in biotechnology or some parts of it, it's exponentially harder to make new discoveries.
So, yes, it's a marriage of the two. I'm involved in a synthetic biology program right now, where that is a lot of what we're facing. It really is, how do you make things scale that we're wet lab limited, little computations on this, and it's hard. But these techniques are being adopted and adapted to make these easier. In fact, we've gone from 2 years ago where we were hardly able to get reproducible results to now having multiple labs producing data and people doing analytics across all. But it's all a human effort. I don't, when I say cybernetics or cyberdyne, there's got to be a human element to it because we're really good at some things. At least I hope so. But I don't know if I completely answered that question, but I think, there's always going to be a human element in all of these pieces.
All right.
That gets us to noon.
Yeah. So thank you very much. Thank you very much, Niall. Thanks everyone for asking questions. If you have additional questions, feel free to put those in the Slack channel. I'll email those to Niall and get some answers for you guys.
And it looks like Scott's ready to go.
All right, Scott, back to you.
All right. Thank you very much, Charlie and Niall. That was great. If you do have questions,